So in the previous module, we saw how we can use backpropagation in order to find the weights of a neural network, of a three-layer neural network. So one of the early success stories of backpropagation was learning to recognize handwritten digits in an address. Right. So this was work done by Jan LeCun back in '89, and essentially they trained a slightly more complex network architecture called the convolutional neural network in order to recognize handwritten digits. You can see the variation in the digits that their network managed to handle, and this did fairly well. Right? So another early success story of neural networks was the Backgammon player built by Jerry Tesaro from IBM, TJ Watson Labs, in 1992. So he built two versions of this backgammon player. One called a Neurogammon, which came in '89, which was essentially a neural network trained using backpropagation in a supervised learning manner in order to play a game of backgammon. So it's like Ludo, if people know about it. So you throw a dice, and depending on the die roll, you move your coins around. So there is a white and a black side. So the idea is to move all your coins off the board by repeatedly rolling the die. Right? So the TD Gammon player essentially used a standard three-layer neural architecture, and was trained using a specific form of what is called reinforcement learning. We'll look at reinforcement learning in a later module, but he used reinforcement learning in order to generate the error signals, and but then use backpropagation to train the weights of the hidden unit, and he managed to build a backgammon player which was able to beat human backgammon champions in gameplay. Right. So these are some of the early successes, and a lot of interest was being spent on looking at neural networks for solving a variety of different problems, right? But then again, people discovered a second drawback with neural networks. So the one thing was that it was incredibly hard to train a neural network because you had so many parameters. You had to tune them, had to tweak them appropriately so that the desired results were obtained. Further, there was this problem called the vanishing gradient problem. So people quickly figured out that if you have many layers in the neural network, right, it was easier for the network to represent more complex functions, even though a two-layer network or a three-layer network, depending on how we count it. The standard three-layer network was an universal approximator, but having more layers allowed more complex representations to be built. But as the number of layers in the neural network increases, the gradient that you compute by doing backpropagation becomes vanishingly small, right? And since there are not enough feedback for the early layers in the network, the weights in the lower layer remains random wherever you initialize them, right? And so you are not able to learn any deep networks, right? So the neural networks that you learn necessarily had to be shallow because only a few three or four layers could be trained meaningfully using backpropagation. So people had to come up with different tricks for training deeper networks. So and this discovery of these tricks for training deeper networks is essentially what has revived the interest in the field. And now we can build networks that have 8 layers, 10 layers, and so on and so forth. And these produce some fantastic performances in problems that were thought to be very hard to solve for AI and machine learning. So there's been this revived interest in looking at neural networks. So I'll talk about one specific mechanism for training multiple layers in a network, and then you can, I mean, if you're interested in this, you can follow it up with other material. So this was proposed in mid 2000s and by Hinton in 2006 and independently by Ashwa Benjia and others in 2007. It's more like a greedy, unsupervised, layer-wise pre-training. So what we mean by this? So you start off with a very simple network architecture called an autoencoder. So you have an input layer, right? And you want to produce the same input at the output. So the input layer and the output layer need to be identical, but in between the connections will go through a smaller hidden layer of neurons. So the idea here is that the smaller layer is going to learn some kind of a encoding or some kind of a reduced representation of the input that is sufficient for you to produce the output that you are looking for. So you could train this using backprop or other slightly more advanced gradient techniques. So if you think about it, there is no real supervision that is required here, because as soon as I have the input, right, the output is just the same input. So I'm going to send it through a smaller hidden layer so that I am learning a reduced representation of the input. Right? So once I have this first level of reduced representation, right, I'm going to iteratively deepen the network. So what I do, so once I have the first hidden layer of representation, I'm going to add another autoencoder network on top of it, right? So this network takes the hidden layer representation for the input and tries to produce the same hidden layer representation at the output, but in the middle layer it's going to have fewer neurons. So in effect, I'm taking this larger input and reducing it to a smaller hidden representation here, and I can repeat this, right? So once I have trained this, I remove the outer layer, right, and then tack on another layer of autoencoders. So now we can see that my training has gone several layers deep. So instead of just looking at one layer deep autoencoder, which I was able to train using backprop efficiently, so I'm essentially using the same construction again and again. So at any point the training happens only on a one layer autoencoder, right? But then because of this iterative deepening, now I have actually taken this input representation and progressively reduced it to a much smaller representation at the hidden layer. So this kind of an observation that you can use this layer wise pre-training of the data led to resurgence in a lot of deep architectures. So why do we call this pre-training? So far I have not talked about any kind of classification task that you are performing. You're just trying to find features in the input space. So once I have found these features in the input space, then I can take this and I can tack on top of it, right? On top of these features that I have learned, I can tack on another neural network, and now I have my full-fledged deep autoencoder, and then this hidden layer representation can now be used as an input to any learning task, right? So this part is called the fine-tuning part, and the layer-wise training part is called the pre-training part, where I find the hidden representation, and after that I can add it to any complex neural network that can do my classification task or my regression task, whatever it is that I'm looking at. So this kind of layer-wise pre-training allowed people to drive more complex compressed representations that were useful in a variety of problem-solving scenarios, right? So this again has revived a lot of hype in neural networks, or in deep networks as they are called, right? So you can see the similarities to the news items that I had shown you from the 1959 thing. So a simulated brain, right, and can teach context to computers, machines that learn without humans, etc., etc. So take what you read in newspapers with a pinch of salt. But again, there is significant renewed interest in deep networks, in neural networks, as there was in the 50s. So, but the overall feeling in the community is that deep learning is come to stay, because there are a lot of nice properties about this generation of neural networks as compared to the earlier generations. So the things are more stable, and things are reproducible, even though significant computing power is needed. So most of these successful applications of deep learning that you see would have had significant amounts of computational power, but then computational power is also cheap, right? And you're able to solve really complex problems using neural networks, right? And so deep learning methods have yielded state-of-the-art performance in a variety of domains like image classification, object detection, language modeling, machine translation, speech recognition, image description. These are the problems that were traditionally considered very hard for machine learning algorithms, and deep learning seems to have a significant impact in these areas. right? So some of the images I used here are taken from the neural networks book by Roll Rogers. So I'd like to show you a few demos of deep networks in action now. So here is one algorithm from the company called Clarify. So which given an image, right, tags it with different kinds of textual labels. So it says that, okay, here given this image, it says there is coffee in it, there is croissants in it, there is a beverage in it, and this is probably breakfast, and it is had in the morning, and overall, hey, this looks like food. So it's able to derive all of these tags just by looking at this image, right? These are all similar images. It has managed to retrieve images that are similar to this. You can see that all of these are images of breakfast, or of a continental breakfast, and all of these have a cup of coffee in there. And so even though the variety of this is able to cover is truly astounding. So likewise, look at this picture here. It's able to figure out that there's a suspension bridge here, and there is a river here, even though the river is not explicitly visible, and that it is night because it's lighted up, and this looks like a bridge in the middle of the city, right? And likewise, it has found similar images, which are all suspension bridges in cities on top of rivers, and so likewise it is able to work on a variety of outdoor scenes and as well as indoor scenes, and it's able to perform really well. And this is the state of the art in terms of image understanding and labeling currently, right? And likewise, you can look at how well it works in machine translation, right? So both the image tagging and the machine translation tasks use a much more complex neural network architecture than we have seen so far. But then, so here is a simple example from here. So I typed in the sentence "What a wonderful idea" in English, and then it gives me the equivalent in French. And not only does it do that, it tells me which words correspond to which word in the translated language, which words in the original English language correspond to uh, which word in the translated language. Right? So I don't know French, so I'm not sure if that's a good translation. So let's not do this. Okay. So let's stop with the previous. Yeah, so it's it and this thing actually can learn translation, can do translations between multiple languages, not just English and French. It was trained on the data from United Nations and European Parliament, so it can do translations between all the European languages. So that brings us to the end of this module on deep learning, and thank you.